Example 4.3. The heat engine uses a polyatomic ideal gas as the working substance. The lower isotherm operates at 300 K. A. What is the Carnot and thermal efficiency of this engine? B. Draw a scaled energy transfer diagram for the situation that includes values of QH, QC, and W. Because this cycle has two isotherms, there are only two temperatures. So that means if I have the Q hot, that's the upper isotherm. And that is TA, TB, and we don't know what that value is. Then we have T cold, which is the lower isotherm. This is TA equals TB, and this is 300 K. And you could see right away, I have an labeling error because this should be C and D. Okay, now that I have that, the next thing that I need to do here is that I'm going to use a bar diagram to identify what is Q hot and Q cold. So what I'm going to do here is that I'm going to come in and I'm going to carry this little PV diagram with me so it's easier for me to sort of put things into perspective. So here I go. I'm going to start off at point A, and I know that that internal energy is the lowest because it has the lowest temperature at 300 K. So then I'm going to come in and I'm going to say, this is my bar, and this is EA. Now, because this is an isotherm process, that means that no matter what I add, in the end, the internal energy of the system cannot change because the temperature doesn't change. So that means that the heating and working must balance each other out. Look at the compression. Because there's a compression, there's an increase in kinetic energy. Let's say it goes up 2 squares. So this is now the work from A to B. And then the heating has to be balanced out. This thing goes from here to here, and this is QAB. So now you can see that there's no change in the internal energy. Now, as I go from B to C, what you're seeing here is that there is an increase in internal energy because I'm going from the lower isotherm to the higher isotherm. So I know that because this is an isochoric, that means that from B to C, there is no work done, but there has to be heating in order to increase the internal energy. So then this is the heating from B to C. So since that's 2 squares, that means then that I have to increase my internal energy by 2 squares. So let's do that. So now my internal energy goes from 1 square all the way up to 3 squares. And so this is my internal energy at C. Now, as I go from C to D, you can see here that this is a isothermal process, which then means that when I look at this, I cannot change the internal energy of the system, and it has to be has to stay exactly the same. So this guy is then going to be ED. So then that means here is that the heatings and the workings have to offset themselves. Now this is an expansion. So the gas gives up its kinetic energy to cause expansion. And you could see that from A to B, that's a smaller area than from C to D. So that means I have to have a bigger work here. So now this is the work from C to D. So if that's 3 squares, then the heating must also be 3 squares. It has to compensate for that. So now this is the heating between C and D, and it looks like this. So now I'm going from the higher isotherm to the lower isotherm. So I have to get back to my initial state. So here is my initial state right there. So that means, because this is an isochoric process, I know that right here, the work from D to A is 0. So then the only way I can get down is that if I take this guy down by 2 squares, where this is my heating between D and A. So now I could then identify what Q heats are. So remember, so Q hot is all the positive heatings. And that implies this is the heat from the hot reservoir going into the gas. And Q cold is all the negative heatings. And this is the heat ejected into the cold reservoir. So it's clear in this situation then that Q hot, all the positive ones you could see is going to be QBC plus QCD. And then I have Q cold. So note that this has to be an absolute value. It has to be a positive value. We've already accounted for the negative sign in the efficiency equation. So then this has to be all the absolute values of the negative heats. So my goal now is to calculate these things. Okay. So now what I need to do here is that I need to look at my curve and then just say, what do we know? So to calculate the maximal Carnot efficiency, as well as the indigent efficiency, we need either temperatures, and in this case, it would be the temperature of A, which we know, which is 300 K, and then we need the temperature of C, which is the same as temperature of D, which we do not know, or we need all the pressures and the volumes. So what we're going to see here is that I know pressure C, I know pressure A, and I know all the volumes. So there are 2 pressures that I don't know. I don't know B and I don't know D. So in this case, we don't know pressure B and pressure D are unknown. So the question is, which is best for you? Do you want to calculate the single pressure TC, TD, or do you want to calculate the pressure B and D? Now, it turns out that they both take the same amount of work. So I would say that to decide which to calculate is a judgment call on your part. Personally, I will choose the pressures and volumes, since isotherms have PV equal to a constant. So I can get the other two pressures because that relationship is easy. So let me show you what I mean by that. So here's my curve now. So I believe I still have this here. So if I look at my curve, I'm going to paste it right over here. Okay, because I got to keep bringing this with me. So now look at the isotherm. So if I look at the lower isotherm, that tells me that I have PA, VA, PB, VB. Note that I have both volumes and I have one of the temp pressures. So then I could then come in and I can solve for the unknown PB, which will then be VA, VB, pressure at A. And so if I compute that, then I'm going to get, this is the volume at A, this is the volume at B. Now note, this is going to be times 10 to the negative 4, but of course they cancel out. And then the pressure at A is 0.85 times 10 to the 5 pascals. So then if I look at this number, I get 9.01 times 10 to the 5 pascals. So now I have my pressure at B. Now I can repeat the process for the higher isotherm. If I look at the higher isotherm, I then have PCVC, PDVD, which then tells me that PD is then going to be VCVD times the pressure at C. So now if I plug in my values, they have the opposite ratio of volumes, but now I have the pressure 40.1 times 10 to the 5 pascals. And when I compute that, I get a value of 3.78 times 10 to the 5 pascals, and this is the pressure at D. Now, I could have calculated the temperature, but I would have said that that would be, that takes just a tiny bit more thinking on my part, and I decided not to do that. So I now have all of the pressures. So now I could then start to go in and calculate all of the details that I know for the whole cycle. Again, I either need the temperatures or I need the pressures and volumes. So now so I'm going to go now and I'm going to do, so the maximal Carnot efficiency is then going to be given by this here. So I have the Carnot is then going to be 1 minus T cold, T hot, And I now know the pressures and volumes everywhere. So what I'm going to do here is that I'm just going to stick to this guy right here, which will be TA is the lowest and TC is the highest. So then I'm going to use the ideal gas trick where I replace that. So that should be PAVA divided by NR and PCVC divided by NR. And what you're seeing here is that you can see here is that I'm going to cancel these. So now it's really just the pressures and volumes that I got to multiply out. So let's plug those in. So if I plug these in, this is going to be 1 minus. Now I'm going to drop all the powers because there's the powers up and below. So here I go. So the pressure of A is 0.850 times the volume, which is 5.10, divided by the pressure of C times its volume, 0.481. And when I compute that, I get 0.775, which then tells me here that in Carnot is 77.5%. So now I know my Carnot efficiency. Now that is a very large efficiency. So now I got to go through the process. And here I go. So now we're going to be looking at the heat engine. The heat engine efficiency, which is eta engine. So we about, as already stated, we know Q cold has to be the absolute value of QAB plus QDA, and Q hot is going to be a positive value of BC plus CD. So Q cold is the ejected heat into the cold reservoir. Q hot is the injected heat from the hot reservoir into the gas. So now let's go calculate Q cold. So calculating Q cold. So let me move this up. And so I'm going to, again, I got to bring my diagram with me. And here's what I know. Here is my cycle. So what I know about the cycle here is that there is heat ejected into the cold reservoir, which is QAB, and this is QDA. So I got to calculate those two quantities. Here we go. So that's the first one that I'm going to calculate is going to be the isothermal cooling QAB. Okay, so that's our first one. So for an isothermal, so we know that for an isothermal, we know that the internal energy from A to B has to be 0. So then if I look at QAB plus the work AB, that means then I can rewrite the heating in terms of the work. So then I know that QAB has to be the absolute value of the work AB. So then if I start to go compute this, remember I'm going to drop the absolute sign, but remember in the end, this is a positive quantity that I must have. So So then the work for an isotherm is going to be written like this. And this is VA, VB to VA. And what you're seeing here is that right now, this is a negative number because VB is smaller than VA, so the log is going to be negative. So again, we want a positive value in the end. So let's go. So if I start putting in my numbers, actually, let me convert nRTA to PA, VA, and this will be the log of VB, VA. So here we go. So now if I start punching in my numbers, I have that the pressure at A is 0.85 times 10 to the 5. Then I have my volume at A, which is 5.10. Now this is going to be, look at this, 10 to the 5 minus 4. So it's really a factor of what? I'm multiplying by 10. So then this is going to be the natural log of 0.481 divided by 5.10. Now again, this is a negative number, absolute value. So when I put the absolute value, I'm going to get 102 joules for QAB. And again, this is a positive quantity. So now I have my first heating. So now let's go to the next heating. Now our next heating is isochoric cooling along path dA. So this is heating at constant volume, so it should be QdA is then going to be NCV, the change in temperature between D and A. And if I start using the ideal gas law, and remember this is a polyatomic, so it should have a minimum of 6 degrees of freedom. Now, if I convert this using the ideal gas law, note that this is occurring at constant volume. So I could factor out the volume part. So I'm going to get 6/2 of PA PD times the volume at A. Note that PA minus PD is a negative number. So I need the absolute value of this. So if I start to punch in my numbers, here's what I get. I get 6/2, and then I'm going to get 0.85 minus 3.78 times my volume, which is 5.10 times 10 to the 5 times 10 to the negative 4, which will give me 10 to the 1 joules. And when I compute that number, remember, this is a positive quantity. I'm going to get 48 joules, and this will be the heating at dA. And again, this is a positive quantity. So now I can then say that the heat ejected into the cold reservoir is Q cold, which is in QAB plus QDA, which is 102 plus 448, which then gives me 550 joules. And that's Q cold. So next now, we have to go in and calculate our other heating, which will then be Q hot. We need to calculate Q hot. So this will be the heat putting put into the gas for that system. So again, dragging my, oops, I need to go get my PV diagram. So let me go put my PV diagram in here. I'm going to make this a little bit smaller. And now that I have that, I need to keep my numbers with me. So remember, this number right here is 9.01, and QD here is 3.78. Those were the pressures that we were missing here. So now if I look at my cycle, here's what I see. What heat is being put in, is going into the gas? There's the heat, the isochoric heating here, and then there's the isothermal heating, CD. So I know that I got to calculate those two heats. So let's go calculate them. So the first one I'm going to do here is that I'm going to do the isochoric heating, QBC. So let's go look at that. This is heating at constant volume. So this will be QBC. It's going to be NCV delta T of BC. Now, look at the volume. It's constant at VB. So then this means that it's got to be this here. So it's going to be 6/2. Then it's going to be the pressure difference PC minus PB times the constant volume, which I'll call VB. So if I now start to put in my numbers, I'm going to get then 6/2. The pressure at C is going to be 40.1 minus 9.01 times the volume, 0.481. Then I have 10 to the 5 times 10 to the negative 4, which gives me 10 to the 1. And that's going to give me joules. So if I compute that number, I get 449 joules for QBC. So now I have my first of the heatings. Now I have the isothermal heating. So now I have the isothermal heating, QCD. So here we'll use the work to calculate that isothermal heating, and it goes something like this now. So let me bring this up. So I'm then going to have that QCD is going to be the negative of the work of CD. So if I compute that, it should be, so remember this is a, going to be nRTC times the natural log of VD VC. So the log is a positive quantity. So it automatically comes out positive. So if I pick the point PC, VC for the temperature, then I see here that I really am calculating this quantity right here. So if I start punching in my numbers, so then I'm going to get what? I'm going to get 40.1 times the volume times, remember, 10 to the 5 minus 4, I get 10 to the 1. Then I have the log of 5.10, and this will give me 0.481. And when I compute this number, I get 467 joules, which then gives me QCD. So now I have all of my heatings. And I could see here is that the heat from the hot reservoir is now Q hot, which is in QBC, plus QCD, which then gives me 449 plus 467, and I get a value of 916 joules for Q hot. So now the last thing I got to compute here is that I got to compute the mechanical work W out. And this we get from the first law. And the first law says that the work out has to be Q hot minus Q cold. And in this situation, I'm getting 916 minus 550, which then gives me a work of 366 joules that the work does for the engine. So now I have this. And so now I can calculate the efficiency. So the heat engine efficiency is then going to be this. I could either write it as 1 minus Q cold over Q hot. But since I've already calculated the work, I can also do it this way. So if I just punch in my numbers, either way, I'm going to get the same answer. I'm going to get here that this guy is really 0.3999, or I can write this 40% efficiency for the engine efficiency. So we could then, in summary, since Carnot is greater than that of the engine efficiency, this does not violate the second law. And that means that at least through the second law, the engine can go. So now let's go draw my efficiencies here. So 40% goes to the goes into work, and 60% is ejected into the hot reservoir. So let's look at that. So if I now draw my energy transfer diagram, what am I seeing? I have a hot reservoir, okay? And when I look at my hot reservoir, I'm going to be transferring 60% to this guy right here. So if I look at this thing, my hot reservoir is then going to be bigger. So I got 1, 2, 3, 4, 5. So I'm going to say, if this is 5, then let me make sure that I'm doing this right. So then what I'm seeing here is that about 2 squares are being ejected, coming in as work here. So now here's what I'm seeing here. So here's my cold reservoir, my hot reservoir, not my cold. So when I'm looking at this thing, this is my T hot, and then this here is my cold reservoir. This is the heat ejected, and this is Q cold. So what I'm seeing here is that I have this very thick heat that is flowing in, which we call Q hot. And this guy's equal to 960 joules. So how much gets ejected into the cold reservoir? According to this, what's ejected into the cold reservoir is 550. Okay, so I got 550. So this is 550 joules. So how much work do I get out of this heat engine? The amount of work that I get out of this heat engine is then I get 366 joules.